This is a review for the AP Physics C mechanics test, and this is Unit 2, Dynamics. So, really, dynamics is just an application of Newton's three laws. And Newton's three laws are the explanation of motion, right? They explain motion at the most fundamental level, why things move the way that they move. And obviously, I know all 190 of my subscribers, you guys are all gonna go get physics degrees and get your go to graduate school for physics. And when you start learning about, Lagrangian mechanics and stuff, you're gonna move away from Newton's three laws. But they're very pivotal in just understanding physics at this basic level. Newton's first law. Newton's first law tells us that an object in motion will stay in motion until otherwise having a force acted upon it. That's just the memorized thing that everyone will tell you, right? Newton's first law is all about inertia, right? So this is the law, it's the law of inertia. And what inertia, inertia, when you hear that an object in motion stays in motion, that's essentially what inertia is. Inertia is just kind of the same thing as mass. It's the idea that an object with mass will continue moving at its constant velocity, right? Remember, velocity has magnitude and direction. An object will move at the same speed in the same direction unless there's a force being acted upon it. So obviously, if an object's at rest and you give it a little force, boom, it's going to move. And if an object's already moving, it'll continue to move, right? There's no force acting upon it. There's nothing keeping it going. It's just that the object has inertia. It has mass. So it's just a fact of the universe, right? It has that tendency to keep on moving. Now, in the real world, that's not really true, right? Like if you stop pushing your Costco cart, it's going to start slowing down. If you turn off your fan, the blades come to a stop. So I thought objects naturally come to rest. Why don't they keep on moving with their original velocity, right? If there's no force being acted upon it. But there is, right? Forces are the key idea of this unit, and forces are everywhere. A force is just an interaction between two objects, right? This is my camera. I don't use this to record. I actually don't know why I just grabbed this. I'm moving around my camera, which it might break, but I'm interacting with this camera, so I'm applying and exerting forces. Oh my god, I shouldn't do that. Forces, interaction between objects, and when you have forces, right, like a frictional force being applied on your Costco shopping cart, it's going to come to a stop, right? That force is opposing its motion. Now, forces don't cause velocity, but they do cause acceleration, right? My frictional force is slowing down my Costco cart after I let it go. But by how much does a force really cause an object to accelerate? Well, that's what Newton's law tells us. It's kind of like an extension of Newton's first law, in my opinion. That's kind of how I've seen it. It tells us that the net force acting on an object, let's do it this way. Let's do it the Ollie the Dazzling way. It tells us that the acceleration due to a net force, right? If there's an unbalanced net force on an object, right? The acceleration of that object will equal the net force of that object over its mass. Or in the more classical way you've probably seen, the F net on an object is equal to its mass times its acceleration. So I like the first way a little bit better. It tells us that an F net causes an acceleration, right? So if I have like a box, right? Are there any forces on it right now? No, there's not. Now, if I apply a force this way, the F net is going to equal F, right? That's the net force. If you were to sum up all the forces, that's what a net force is. That's F. Now, if there's some force in the opposite way, we'll call this F1, and then we'll call this force F2. Now, the net force, you have F1 this way, and then you have F1 the other way. So, or F2 the other way. So the F net is going to be F1 minus F2. You could also say F2 minus F1, right? You can decide which, like if F1 is bigger than F2, you can say that the right side is positive so that you get a positive F net. It's up to you though. So then I could set this equal to MA. So I can say MA is equal to F1 minus F2. That's where the second version comes in handy. So that's Newton's second law. It helps us find the acceleration given the mass. And Newton's third law, this is, I think, the most unintuitive, is that, hey, if you have two objects interacting with each other, that's what a force is. Well, the force, I'm not going to verbally write it because I hate the reaction nonsense. I like this way better. If I have object A exerting a force on object B, let's do it like this. Let's use multiple colors. So let's say we have A. Let's do it like this. So actually, no, it's fine. We don't need different colors. If we have object A and object B, Newton's third law tells us that the force on object B by object A will equal in magnitude the force by object B on object A. These are equal forces, and they're opposite in direction. Well, that kind of looks like it makes sense. They're the same, size, and they look like they'd be the same mass, so it would make sense that they exert equal forces on each other. But it's always true. If you had a car hit a mosquito, it would seem like the heavy car is probably exerting one hell of a force on that mosquito. But the forces are still equal and opposite. Always. Newton's third law always holds. I think. If we did a classical experiment where Newton's third law didn't hold, I would ask someone to give that guy a Nobel Prize because it always holds. Now, in this case, right? Well, if they have equal forces on each other, why does a mosquito get splattered on the thingamabob, the windshield, and just keep on moving while the car is unaffected? Well, it's this equation right here, right? For a car hitting a mosquito and a mosquito hitting the car, their F net that they each experience is the same, right? For the mosquito, it's the force by the car. For the car, it's the force by the mosquito. Equal and opposite forces. So for the same force, a really big, massive car will have a really small acceleration, right? Or this way might be better, right? Or no, I think this way is... Yeah, actually this way is better. F net is the same, so a really big M in the denominator will be a really small acceleration. Mosquitoes have a very small mass, so they get a really big acceleration. So that's why Newton's third law actually explains a lot of phenomena, and especially when we get to units 4 and momentum and stuff, with collisions it'll make more sense. Okay, so those are Newton's 3 laws. Let's talk about common types of forces. First, I just want to talk about the normal force and the tension forces. So if you think about an object, sitting on a table, right? There's obviously, I know we haven't gotten to gravitational force, but hopefully you have an understanding that, there is a weight force, right? Earth is pulling you down. Well, hey, based off this FBD, you should be crashing down through the table. Well, no, the table is pushing up back on you. So this is what we call an FN, a normal force. Now the normal force, in this case, it would be equal to Fg, right? Because I know that my F net on the block is 0. It's not accelerating. So the Fg needs to equal the Fn. But that's not always true. Fn doesn't necessarily need to equal Fg. It's an adaptive force. If I were to push down on this block, Fn goes up, right? If I were to pull up on the block, well, the forces need a balance. So there's more upward force. The Fn needs to go down, right? So that they both balance out the Fg. And you know, that's the normal force. It adapts. I, you know, on a, I don't. So you know, people say like, oh, the quantum force is like the, you know, the molecules repelling each other on contact, and you'll probably break it down like that quantum level. But you know, we just know that the normal force is an adaptive force. It changes. Same thing with tension, right? If I have a block hanging, right? If I pull down, then the tension will go up because that tension force needs to balance out now the Fg and my downward force. If I kind of lift the block up, then the tension force will go down. So those are both adaptive forces. Let's talk about the frictional force. So friction is actually proportional to, it's really interesting. Your friction is actually proportional to your normal force. So one key idea is that normal force is always perpendicular to a surface. Hopefully that kind of makes sense, right? Like if I had a whiteboard and I start pushing on it, yeah, there's going to be a normal force, right? This surface is exerting force on me. That's what a normal force is. But no, it's not going to point up. It's going to point perpendicular. It's going to point against my fist, right? Because it's always perpendicular to the actual surface. So for frictional force, there's static and there's kinetic friction, right? So static and then there's kinetic. I think kinetic's a little bit more simpler. The kinetic frictional force tells us that kind of the equation is that force of friction is equal to your Fn times a certain constant of cofriction, mu k, and you know this will always be a number less than 1, right? So if it's 0, that means there's no friction, right? Because any normal force times 0 would just be 0. If it's 1, that means your frictional force is equal to your normal force. I don't believe it can go greater than 1. Not that I've seen in this class. Actually, can it? No, I don't. When you get into AP Physics 2, you deal with so many constants you forget, because like it's the index of refraction isn't less than 1; it's always greater than 1. So I do believe it will always be less than 1 though. And this equal sign in the equation tells us that it's a constant force. So if let's say this is my friction force right here, right? And just so that there's got to be an Fn, there has to be an Fg, right? If I increase this force, the friction force stays the same because it only depends on your normal force. It's proportional to the normal force. If I push down, if I add another push force down, then my friction force will go up because my normal force has to go up, right? In order for all the forces to be balanced in the y direction, right? So now when you're dealing with 2D stuff, it's like in the x direction, there's going to be acceleration. In the y direction, it's going to have 0 acceleration. Now, static friction is actually another dynamic force because, did I say dynamic? Adaptive, that's the word. It's another adaptive force. Force of friction, static, will actually always be less than or equal to Fn times mu static. So mu static is another coefficient. Your static friction can vary, right? Static friction is when your object is not moving. I forgot to define that. I'm so sorry. Kinetic friction is like when your object's moving, but when your object's not moving, if you give it a little force push, the static friction force will kind of be in the opposite direction, right? If I give it a large push, then hey, it's going to adapt until it reaches a breaking point, right? Once my push force exceeds Fn times mu, its absolute maximum, then it's going to start moving. So that's static and kinetic friction. For the gravitational force, the main thing to kind of understand is that objects with mass attract each other, and the equation to figure out how much they attract each other is G, the universal constant, 6.67 times 10 to the negative 11 Newton meters squared over kg squared, right? If you think about the units. Fg is equal to G times m1 times m2 over the distance of separation, d squared. Now, that means that as you change your distance from, so if you had two masses, as you change your distance, right, if you increase the distance, the gravitational force decreases. So that would mean, right, like if you're on the top of Mount Everest, aren't you like farther away from the Earth, right? The distance you're really measuring, by the way, right, it's the center of masses, really. So if I have two objects, I'm measuring the d from the center of masses. So if I move farther away from the Earth, you would think that, well, your gravitational force should decrease. And it does, like a very, 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 very small amount. On here, at this scale, Earth's gravitational field is roughly constant, right? So in this case, you can kind of express, that, well, Fg is really equal to m times g, right? So m times g is a gravitational force, and g represents the gravitational field strength, which on Earth is 9.8 newtons per kilogram. So obviously, if you increase your mass, you would increase your weight. And you can solve for g, right? If you set these two equations equal to each other, you get that g, when you drop the m's, it's just gm over d squared. So you can actually plug in Earth's radius and its mass, and you can figure out that it is indeed 9.8 meters per second squared. And this is also why, if you connect this back to Newton's second law, why all objects in free fall accelerate at the same rate. It's why they do that, but really it's, the masses drop, and at a more conceptual level, that still wouldn't please Einstein. When you increase your mass, you have more inertia, so you're harder to accelerate, but you're also getting more gravitational force. So that's why that happens. Centripetal force. Now, when you're moving, Newton's first law tells us that if you're moving in a straight line, the only way you're ever going to change that direction, right? The only way you're ever going to stop moving in a straight line is if you have a force exerted on you. And centripetal forces, it's a whole unit of study in AP Physics 1, but for dynamics, we kind of just bundled it into this unit. Hey, centripetal forces, they cause circular motion, right? So if I have an object moving in a circle, maybe on like a race car track or something, right? It's moving tangentially to the circle, but there's that Fg that's always pointing to the center, right? So no matter where it is on its path, that, not Fg, but just some centripetal force that always points to its center. Now, we can relate the centripetal net force to the centripetal acceleration. So F net C is going to equal m times centripetal acceleration. Now, this is a different kind of acceleration because it's not your speed changing, it's your direction changing. So you can play around with some vectors, and you'll find that the centripetal acceleration actually ends up being v squared over r, right? So if you increase your speed, changing that velocity direction, if you increase your speed, the change in velocity vector, right? That's just what acceleration is. It becomes greater. If you decrease the r, your change in velocity, your change in that velocity vector becomes If you decrease r, your radius of the radius of that path, your change in velocity vector becomes bigger, because you can see if I go at a certain r and then I go at a smaller r, my velocity vector represented by that pen changes a lot more. If you take the limit as r approaches infinity, well, that's just when you're moving in a straight line, right? Because as your r gets bigger and bigger, it just kind of looks like you're moving in a straight line. As r approaches infinity, centripetal acceleration becomes 0 because you're essentially moving in a straight line, right? If you think about a super infinitely large circle. That's centripetal force. Now, this is really all of dynamics in this unit, but I'm going to go over 4 example problems that kind of help us understand and put these concepts into play. So let's go over them really quickly. I want to kind of get through them quickly because I understand that you can click off now if you feel like you understand everything, but these problems kind of show all of these concepts in play. So first kind of example problem that you might see on the AP test is a coupled system. So let's say we have a ramp. So let's say we have a ramp, inclined 30 degrees, and we have a 5 kilogram mass on top of it, linked to a pulley, which is massless, to another 40 kilogram block. And let's say there is friction on this ramp, so there's going to be mu k, right? Your static or kinetic friction is going to equal 0.2. And let's try to find, well, what is the acceleration of this system right here, and what is the tension in this rope. So hopefully you can kind of predict that, like, the whole system will kind of accelerate this way, right? I mean, like the 40 kilogram block is literally 8 times the weight or mass of the 5 kilogram block. So the whole thing will probably, even with friction, right, accelerate that way. And let's figure out, well, how are we gonna kind of see that? So you could draw your FBDs, right? So an FBD, by the way, is just a free body diagram where you draw your forces on an object. So for the 40 kilogram block, so for 40 kg, you have your FG pointed down, and you have some tension going up, and we know the overall acceleration is going to be downward. So we know FT is a little bit less than FG. And then for the 5 kilogram block, you have your FG still pointed down, but now you have a normal force that's at an angle. And then we also have tension pulling this thing up. Then we have friction. We have friction going the other way, right? Because it's moving and accelerating up. Well, moving up, right? You can accelerate up with friction being down. Maybe, I don't know. Or with, yeah, you can accelerate. Yeah, I would have to think about it some more. I don't know. Point is, friction points down the ramp. So, because you're moving up the ramp. It's always in the opposite direction of motion. That's another thing. Kinetic friction is always in the opposite direction of motion. So if we want to find the total acceleration, we can actually, for the whole system, we can do a little trick. We can say, well, hey, the total acceleration of the system will just equal the F net on the system over the total mass. So what this means is the tension forces that these two blocks exert on each other, they're an internal force. They're not external to the system. You can't apply a force on your own system, right? Only external forces can do that. So we are looking at, well, what objects would be causing an external net force? There's obviously gravity, right? So we can say, well, there's going to be a net force of gravity pulling us down. So 40 kg, or 40 times 9.8. And then we would also have the friction force on the 5 kg block and the gravitational force. So for this, what you would have to do is reorient your axis for the 5 kilogram block, right? So for the 5 kilogram block, on this incline, there's Fg, and there's a normal force. And a geometry exercise you can do is show that this normal force is actually, oh no, we don't want to split the normal force. I'm so sorry. This gravitational force, if we reorient the axis, let's say x is this way and so x is parallel to the ramp, y is perpendicular to the ramp. Well, there's going to be now an Fg y component and an Fg x component, right? When you split up your thing, your forces. So an exercise you can do is show that this is 30 degrees right here, the angle of inclination, that this 30 degrees equals that 30 degrees. And we get that, well, the force that's kind of, against the tension, right? The force that's kind of down the ramp causing this tension, that's FGX. So it would be 5 kilograms times 9.8. That's the total FG, but we want the X component, so we have to tack on that sine 30, which is luckily 1/2, but we'll leave it as sine 30 degrees. Now for the frictional force, it's going to equal Fn times mu. So mu is going to be 0.2. For the Fn, Fn is just equal to Fgy, and Fgy is just equal to F, right? Because in the y direction, the forces are balanced, and then Fgy is just that weight multiplied by cosine 30. So 5 kilograms times 9.8 times cosine 30 degrees. Woo! All over the total mass of the system, it's 45 kilograms, right? 40 plus 5. So now we're gonna see, and we're gonna see kind of how this plays out with our calculator. 40 times 9.8 times, or minus 5 times 9.8 times sine 30. We're on degrees, or we're radians. Okay, let's change it to degrees. So 40 times 9.8 minus 5 times 9.8 times sine 30 minus 0.2 times 5 times 9.8 times cosine 30. And that gives us a certain net force, divide that by 45. That gives us an acceleration of about 7 I can write this down. So that gives us an acceleration of about 7.97 meters per second squared, which is kind of close to 9.8, right? And that should kind of make sense because this block is mostly in free fall. It just has that 5 kilogram mass kind of weighing it down with a pretty low coefficient of static friction and also on an incline. So it's kind of close to free fall. Now, if you want to find the tension, well, now you can't really treat this, you can't really deal with this in one whole system. You got to split them up into separate systems. And, by Newton's third law, we'll know that the forces that they exert on each other will be equal. So it doesn't matter which object you take, but I could just say that, hey, well, the net force on the 40 kilogram block is going to equal 40 kg times 7.97. And then the F net is just going to be Fg minus Ft. Is going to equal 40 kg times 7.97. And then I can do 40 kilograms times 9.8 minus 40 kilograms times 7.97 equals Ft. And then I will get my Ft, which is 40 times 9.8 minus 40 times 7.97. So that would give us 73.2 newtons. So now for the next example problem, we're going to look at elevators. So with elevators are pretty interesting. So we have a guy on this elevator, right, for this problem. And we need to find his true weight. What we know is that when he's accelerating upwards in this elevator, when the elevator is accelerating upwards, he's on a scale, and this scale reads 750 newtons. When he's accelerating down with the same magnitude of acceleration, then the scale actually reads 650 newtons. So what's his true weight, right? First of all, why is the scale reading changing? Well, your scale reading doesn't tell you your Fg, it tells you your Fn, right? So when you're in just a inertial reference frame, meaning you're not accelerating, right? And you're standing on a scale, and as long as you're not being pushed down or pulled up, hey, your FG equals your FN. So it just accurately tells you your FG because it is your FN. But when you're accelerating up, your FN's a little bit bigger, right? Than your FG. When you're accelerating down, in order to accelerate down, your FG is a little bit bigger than your FN. So that's why the scale reading would be a little bit lower. It's showing the FN, right? Or when you're accelerating up, it's a little bit higher. It's showing your FN. So we can use Newton's second law to figure out your true force, because what we know, or true weight, sorry, because what we know is that FN minus FG is going to equal MA. And then in this case, FG minus FN is going to equal MA, right? And these are all kind of looking at magnitudes. And what we know is that, oh, actually scratch what I said about magnitudes. Don't confuse yourself. That's not what I meant. Okay, whatever. Point is, this MA right here is going to equal that MA because the magnitude of the net forces are equal. That's kind of what I was trying to say. How do I know the magnitudes of the net forces are equal? Well, it's the same magnitude of acceleration. So I can actually just set these two equal and then solve for FG, which is the true weight. So I can say FN, 750 newtons minus FG is equal to 650 newtons. Sorry, whoa. FG minus 650 newtons. And solve for FG. So I can add the 650 over. That gives us 1400 newtons. Is going to equal to FG when I add one of the FG's over, and then I get FG is 700 newtons, which would be his true weight. Kind of the middle between the two. All right, so for the third example problem, we're going to actually derive Kepler's third law. And the point, I'll make another video actually. I'll probably make like a unit 3.5 video on gravitation. So I'll talk about more of Kepler's law there. But main thing with Kepler's law, Kepler's third law is the process, right? The process of setting up your FPD, the process of doing all that fun stuff. So let's say we have a planet and we have something orbiting it, like a comet or something, and this is a distance of separation r. And this is a mass m. This is a mass m. We want to figure out the period. Actually, let's make this a, just for fun. So in order to find the period, we kind of need to know the speed, because the period, if we think about the period is going to equal the total distance it travels, which is really 2 pi a, over the speed this comet travels at v. Well, how do I find the speed v? I can actually use my circular motion stuff, right? Because I know that, well, the F net on this FG is causing the comet to move in a circle. So I can say FG is equal to m times the centripetal acceleration. I can do my m over a squared is going to equal m b squared over a. Couple things happen. One of these a's drop, because I have an a squared and an a in the bottom, and the m's drop. And what I get is I get v squared is equal to g m over a. So, I have a v, I don't really have a v squared, and I don't really want to deal with the square root. So let's just square everything, because why not? So that I get a v squared I can substitute in. So I get t squared is equal to 4 pi squared a squared over gm over a. And I have a fraction in the bottom, so I just take that reciprocal, and I get t squared is equal to 4 pi squared over gm times a cubed. So really, this is Kepler's third law. It tells us that the orbital period is proportional to the cube of a. And the main kind of takeaway is that when you increase your orbital radius, right, or your orbital distance from the planet or the sun or whatever, your period increases. And that should kind of make sense, because as you move farther and farther away, there's less of an FG on you. And if there's less of an FG, right, and less of a net force on you, because FG is the only force when you're in that orbit, approximately, less FG means you got to move slower, because to move in that circular path, you would need a slower speed because you have a slower gravitational force on you. So the t squared and the cube stuff, that just comes from math, but the conceptual idea that as a increases, so does t, that's kind of the thinking behind it. Now, for the last problem, to kind of review for this unit, let's say we have an airplane. And let's say this airplane, it's a nice propeller plane, and it's a cool little plane. And let's say that it's in a it's moving in a circular path, right? And like this angle right here, it's banked at like 40 degrees above the horizontal, and it's moving at a speed 480 kilometers per hour. So if you look at a top view, right? If you look at a top view, it's just moving in a circle, and we're asked to find the radius of that of this circular path. Seems like a challenging problem, and also let's say that the lift provided, it's like an aerodynamic lift that is perpendicular to the wings. So there's this F lift. Now this seems like a pretty hard problem because we're not even given mass. We don't even know the mass of this thing. So when we do F net equals mv squared over r, we're kind of in a pickle, right? We got to figure out, well, what is, first of all, the F lift, and then we got to take the component, because if you do your geometry, okay, wait, this is kind of, so let's draw it like this is a plane, right? So if this is 40 degrees, then this is 40 degrees. So then this right here is 40 degrees. And then if that's 40 degrees, then this would be 50 degrees. So this would be 40 degrees. Oh boy, right? So that 40 degrees is right here. So we could split into its components and stuff, but we don't have mass. But the nice trick that makes this a question so nice is that this F lift is doing two things. It's keeping us moving in a horizontal circle, but it's keeping us moving in a horizontal circle, right? It's moving us in a circle, providing that centripetal net force, but it's also keeping us aloft, and it's not making us fall. The y component of that F lift, right? F lift cosine 40 is going to equal FG, right? F lift cosine 40 equals FG, and I know that F lift sine 40 will be the centripetal net force that kind of points in the middle of that circle. So we'll call this F net. Well, I don't know what F lift is, but that's fine, because I know that, well, F lift is just going to equal, when I solve for it, it's going to equal mg over cosine 40 degrees, right? So F lift is equal to mg over cosine 40 degrees. Now I can substitute that back in, and I get mg over cosine 40 degrees. It's going to equal, or multiply that by sine 40 degrees. We get will equal the F net, which is going to equal it's going to equal mv squared over r. But the main thing is, well, sine over cosine, that's tangent. So it's mg tangent 40, right? So I can substitute that back in to my original equation. And you can see the m's are going to drop, right? So mg tangent 40 degrees is going to equal mv squared over r, which is what we're solving for. The m's drop, which is pretty nice. And we know v, right? So we can solve for r. So we can solve for r. R is going to equal v squared over g tan 40. The main thing with this problem is just converting kilometers per hour to meters per second, right? So you can do it like this. You could say, well, 48 out. Well, there's 3,600 seconds in an hour, right? Because there's 60 minutes. Each minute has 60 seconds. So if I multiply this whole thing, kilometers per hour, and I want it to be in seconds. So if I do 480, divide that by 3,600, that gives us like 0.1333 or something like that. And that tells us that in 1 second, it travels 0.1333 kilometers. And that would be the same as multiplying by 10 to the third. That's 133.33 meters per second. So that converts to 133.3 meters per second. Square that, divide that by 9.8 times tan 40, and that gives us about 2,000 meters if I show you my calculator. So yeah, that's dynamics. Thank you for watching.